Hello, this is Jack Jackson. In this video, we're going to talk some more about using matrices for transformations. And we're going to be focusing it here on the group structure of transformations. And so if we use three-row matrix versions that we talked about in the last video, then the algebraic structure of both isometries and similarity transformations has the structure of a group. Recall that a group is a set G, in our case, transformations or the related matrices, and a related binary operation, composition of transformations, functions, or the related matrix multiplication, in our case. And the groups are subject to the following definitions. So here's the basic definition of a group. Given a set G and a binary operation star, we say that G star forms a group if and only if. Well, this next line you really don't need to say because when you say it's a binary operation, this is what it means. The star is a function mapping ordered pairs of G into G is closed. That is, for every element A and B and G, A star B is a specific element back in G again. Okay, it's a function, but it's also closed, so all the outputs are back in G. So with that operation, it's associative. That is, if you take A star B, do that first, and then start with C, you get the same thing as doing B star C and then A star that product. And that has to be true for every A, B, and C in your group. Next, there has to exist an identity element, let's just call it E here, in our set, such that E star A equals A star E equals A for every A and G. And every element must have an inverse. For every A and G, there exists an inverse element, Z, so that A star Z equals Z star A equals E. Now the following table is going to talk about these properties. So these properties here are exactly listed in those four properties are actually listed right there. I'm using some math notation for some of these. I'll explain the symbols as we go along. And then over here, we're seeing how we can see that similarity transformations, both as a transformation, how these properties apply, and how these properties will apply when we're working with matrices. And these are going to turn out to be isomorphic ways of doing that. So first of all, the first property up here is that we have to have a binary operation. So for every two elements, this time I'm using a dot for the product, it has to be back in the element. And this is for every U and V, which is an element in our group G. Well, how does that satisfied or what does that mean in our context? Well, composing two similarity transformations in G also produces a specific similarity transformation in G. A subgroup of that is the isometries. The composition of two isometries produces another isometries. Matrix multiplication of matrices in G yields a specific matrix back in G. So G is going to be a specific set of 3 by 3 matrices that represent similarity transformations, or another specific subset of that represents isometries, and those sets are going to be closed under matrix multiplication. So when we multiply two matrices, we get a specific matrix back in the set of matrices that we want. Associativity, this says U times V grouped together first, then times W is U times V times W. I need to be consistent on my operation. I'm not at all. Let's go ahead and use the star for the operation. Okay. And again, this is for every, that upside down A is for every U, V, and W. That version of an epsilon is an element of G. So what this means over here is this composition of functions is associative. Composition of functions in general is associative. We proved that before. And so transformations, that's going to be associative, including similarity transformations, isometries. Those are all going to be associative functions under composition. Well, matrix multiplication is also associative. We showed the proof of that, kind of messy proof, but we showed that in the last video. There has to be an identity element. So this backwards E looking thing is there exists an E, an identity element, which is an element of the group G. And this one here is such that E operate U is the same as U operate E, which is back to U again. And this has to be true for every U and G. Well, we know what it is. In transformations, the identity transformation leaves the transformation that leaves every point fixed. When it's composed with any other transformation, that transformation, you just get the other transformation. Okay. In matrices, the identity element is this for 3 by 3 matrices. Ones along the major diagonal, zeros everywhere else. 1, 0, 0, 0, 1, 0, 0, 0, 1. Multiplying by that matrix on either side leaves that matrix fixed. We proved that in the last video. And then we also need to have that every element has an inverse. Okay, so the way this works is for every U that's an element in G, there exists an inverse element, which we'll use this notation now. U superscript -1, that's the inverse of U, has to be an element of G, such that what happens? Well, if you take U and do the operation of that with U inverse, or you do U inverse operate U, you get the identity element, which I've been calling E, so I'll leave it E. So how does that relate to transformations? For any similarity transformation, there is an inverse similarity transformation in the same group of transformations. We've seen that in earlier videos. We've talked about what the inverses are. We know, for example, the inverse of a translation is a translation by the opposite vector and so forth. We know every one has an inverse. So square matrices with non-zero determinants turn out to have multiplicative inverses, and we talked about that in the last video. So this tells you that we have a group structure both for matrices and for transformations, and if we pick the right set of matrices, then they actually correspond exactly with the sets of transformations that we're talking about, whether that's dilations, as well as reflections, rotations, translations, and so forth, or if it's just the isometries. Okay, groups are studied obviously right now in college geometry, but they're especially studied in abstract algebra and group theory, which is part of abstract algebra, and perhaps in other mathematics classes. Keep in mind these groups of matrices and transformations as examples in these classes. In fact, this entire last chapter of this college geometry text, this entire playlist, is also appropriate as a portion of an introductory course in abstract algebra, particularly this last section on the matrices part. And the group structure here is easiest to use compared to the vector space structure we're going to show you in the next section, the next video, because you only have to keep up with a single operation, matrix multiplication, and it relates more directly to transformations. If you're in my class, you may have some final exam questions over some of this material. If so, it will focus on the group structure version we're using here with 3 by 3 matrices. Now, in subsequent sections, we'll give the form of the transformation matrices for translations, rotations, reflections, glide reflections, and dilations, and we'll show exactly how these things line up exactly with our transformations. In the next video, there is an alternate structure it's a vector space structure, and we'll talk about that in the next video.